Thank you for sticking around and coming to my talk. I want to start by saying that I work in quantum computing. So if I'm saying something that doesn't make sense, going too fast, using some jargon, do stop me. The results that I will tell you about are from a couple of papers, and these papers have some subsets of these authors. So I want to tell you about these few physics-inspired variants or relaxations of the graph isomorphism problem. Of course, graph isomorphism is this prominent problem in or relational graphs in discrete math, right? And the idea is that, well, we say that two graphs are isomorphic if they are the same, but perhaps we've labeled vertices. But if you wanted to prove to someone that two graphs are indeed the same, well, there are several ways how you would do it. One would be by exhibiting this isomorphism map, this function f, right? That tells you how to match up the vertices between the two graphs. And we want this f to be a bijection, so it's going to take vertices of my graph G to that of H. And we wanted to preserve the structure of the graph. So we wanted to preserve the adjacency and non-adjacency. And I'm going to denote isomorphism of two graphs using this congruence symbol. And when I'm going to talk about some relaxation or variance of graph isomorphism, I'm going to put subscripts to the congruence symbol. For instance, Q for quantumism. All right, perhaps your favorite way of thinking about graph isomorphism is in terms of adjacency matrices. Right, and in that case, two graphs are isomorphic. Precisely, we can find the permutation matrix that conjugates the adjacency matrix of one graph to that of the other. And of course, this conjugation I can also write in a slightly different way, right, where my permutation matrix appears on both sides of the equation. And sometimes I'm going to refer to this as the matrix-based definition of graph isomorphism. Now, to get to these physics-inspired variants of quantum isomorphism, I need yet another way to think about isomorphism, and that's going to be via nonlocal games. So you've already seen nonlocal games in David's mini course. So this will be somewhat similar, but it's going to capture graph isomorphism rather than homomorphism. The intuition behind this game, like how we want to design this game, is that you should think that it's some sort of interactive protocol through which these players, Alice and Bob, they're trying to convince the verifier that two graphs are isomorphic. Right? The game proceeds as follows. So the referee or verifier, he selects two vertices, x and x prime, and these could be vertices of either of the two graphs. For simplicity, let's assume that the vertex sets of the two graphs are disjoint. And then Alice and Bob have to respond, again, with two vertices. All right, and afterwards, they will win or lose this game together as a cooperative. And what are the conditions that are going to make them win the game? There will be two such conditions. The first one says that, well, let's look at Alice. If Alice receives a vertex from graph G, she should respond with a vertex from the other graph, so graph H, the other way around. And so she gets a vertex from H, she must respond with a vertex from G. And the same for Bob. I also wrote down the game here in case you at some point start thinking, what was this game? And now that if this condition is satisfied, then each player has one vertex of G and one vertex from graph H. And the next condition says that the player's G vertices should be related the same way that their H vertices are related. What do I mean by related? Well, if I take two vertices from the same graph, I'm going to say they can be related in one out of three ways. They could be the same, they could be distinct, non-adjacent, or they could be adjacent. So for example, if the referee selects two non-adjacent vertices of graph H and sends them to Alice and Bob, then in order to win, they must respond with two non-adjacent vertices from graph G. There are some more complicated cases where one person receives a vertex from graph G and the other one from graph A, but it's all captured in this condition. So now the question we would like to understand is, for which pairs of graphs can Alice and Bob win this game, irrespective of which vertices the referee chose to send them? What do Alice and Bob know and what don't they know? Well, they know the two graphs G and H, and they know the rules of the game. They know what kinds of answers will make them win or lose this. What they don't know is what the other guy received. So Alice only sees her vertex, and of course she knows her answer, but she doesn't know what vertex Bob received or answered. Okay, usually we express this by saying, well, Alice and Bob are not allowed to communicate after they receive these vertices, x and x prime. Now, one thing that is relatively easy to prove once you understand what precisely these strategies are. So basically the strategies for Alice, you could say that they correspond to functions that map these vertices V, P, and Bob has some other function. Once you formalize that, then you can see, well, the players can win this game precisely when the two graphs are isomorphic. Okay, so in fact, we made the rules of this game so that this statement would be true. Okay, but once I put up the definition of the game, then this fact is something you prove. It's a statement you prove, right? Not define. But now this kind of allows me now to talk about other variants of isomorphism by fixing this game the same, but giving Alice and Bob more power, more strategies that they can use. Okay, so in particular, I'm going to talk about quantum and non-signaling isomorphism. And this is defined as the ability of quantum or non-signaling players to win this game. And now, what are quantum strategies and what are non-signaling strategies? I'm about to explain that. Well, quantum strategy is going to be a triple. Perhaps you already saw that, hopefully, in David's mini course. So I'm not saying something completely new. So it's a triple. I also wrote down it up there. So it consists of quantum state, which is just a unit vector and some bipartite space, so some CD, tensor CD. And then you have measurement operators for Alice and Bob. Operationally, what is going on? Alice and Bob are sharing the state. Now, Alice receives a vertex, and then she performs the measurement on her part of the state that corresponds to that vertex. And we can assume that the measurement yields another vertex, which then Alice sends back to the referee. And Bob acts similarly, but his measurements could in principle be different from Alice's. Okay, so this quantum state is just a unit vector. And now these measurements for Alice and Bob, they are given by positive semidefinite operators that add up to identity. Okay, so I have these matrices, positive semidefinite matrices, EXY and FXY, where X and Y are vertices. They play according to such a strategy, then quantum mechanics tells me how to compute the probability that given questions X and X prime, Alice and Bob respond with Y and Y prime respectively. Okay, and that's given by this inner product. Okay, so remember, like this measurement, it's a probabilistic process. So what you get is a probability distribution over these vertices, these Y's and Y primes. And again, we would like to ask the same question: for which graphs, which pairs of graphs G and H can now quantum players win? So what does it mean that they can win? Well, it means that I can pick this triple, the psi and the E's and the F's, so that the probabilities that correspond to them losing in the game are zero. And unfortunately, this is a very hard question. And the basic difficulty lies in the fact that I don't know in which dimension D should I be looking for. So how large these matrices should I look for? Now, one common relaxation that people in quantum community look at to overcome this difficulty is the so-called non-signaling strategies. So if you have some quantum strategy, so you have this triple, right? And then you think about this joint conditional probability distribution or set of such distributions P, then it turns out that this always satisfies the so-called non-signaling conditions, right? So non-signaling conditions say that so if you fix Y and X and you take a sum over Y prime, then this is constant for all values of X prime. So one thing that it's saying is that Alice is marginals, right? So what's the probability that on question X, Alice is going to answer Y? It's saying that these marginals are well defined, so they don't depend on the question that Bob received. And the same for Bob. Okay, and kind of the physical principle it's trying to capture is that this probability distribution P does not allow Alice to send information to Bob and vice versa. And then non-signaling strategy is just any probability distribution P that satisfies these above two conditions. Okay, and remember we defined non-signaling isomorphism as the existence of such non-signaling strategy, right? So we are asking for a probability distribution P that satisfies these two conditions and has zeros in those spots that correspond to losing answers. And next, I will try to relate this non-signaling isomorphism to some terms that will probably be very familiar to you. Okay, so let's assume that we have two graphs, G and H, and they are non-signaling isomorphic, and we're going to build some matrix D. I'm going to define the G8. So the rows of my matrix are going to be indexed by vertices of G, the columns by vertices of H, and I define the GH entry to be equal to this probability. Turns out that you can use the non-signaling conditions and the winning conditions to show the following two properties of this matrix D. First, we can show that D is doubly stochastic. And second, you can show that it satisfies this relation with respect to the adjacency matrices of the two graphs. Now, do these conditions remind you of something? Right. So they somewhat remind you perhaps of isomorphism, or did I hear some other words as well? Yes, fractional isomorphism, right. So indeed, right? So this is some relation that is well known on graphs, right? So it's fractional isomorphism, and two graphs are fractionally isomorphic. I'm denoting its congruent sub F. If you can find a doubly stochastic matrix D such that this relation is satisfied. Okay, and so what we saw, this previous construction of this matrix D shows is that non-signaling isomorphism implies fractional isomorphism. And of course, now it's natural to ask, well, does the converse hold as well? Right, and indeed it does. To reach the converse, we need to use this very nice characterization of fractional isomorphism by Ramanujan, Steinerman, and Ullmann that says that two graphs are fractionally isomorphic precisely when you can find a common equitable partition, right? And basically, we use this common equitable partition to define a winning non-signaling probability distribution. And then that shows you the converse simply. All right, so then what we get is that this non-signaling isomorphism is actually the same as fractional isomorphism. And we get some extra things because of what is known about fractional isomorphism, right? So it's also equivalent to the two graphs not being distinguished by the so-called one-dimensional Weisfeiler-Lemon algorithm. This is some algorithm that serves as an efficient test for graph isomorphism. Okay, so I'm saying it's a test. So if it says that the graphs are not the same, they are indeed not the same, but the other answer is inconclusive. All right, and it's also equivalent to the two graphs not being distinguished by any formula in two-variable counting first order logic. And we get further these corollaries that non-signaling isomorphism can be tested in polynomial time. Well, because this Weisfeiler-Lemon algorithm, for instance, runs efficiently. And we also know that, well, it can distinguish almost all graphs also. These statements are true for fractional isomorphism, so they are true for this non-signaling isomorphism, which is the same. So these last two bullet points pretty good, right? But so there are also shortcomings, right? So we cannot use non-signaling isomorphism does not distinguish these two graphs, right, which are very different. One is connected, the other one is not. And more generally, if you have any pair of D-regular graphs, say it's going to fail to distinguish. All right, but well, as far as non-signaling isomorphism goes, we have sort of understood it because we have shown that it's equivalent to the fractional one. So we can go back now to this quantum isomorphism and see what we can say about it. So this was defined as the existence of a winning quantum strategy. And this was what the strategy is. What we can show is, because of the structure of the game, we can show that we can simplify the strategy slightly. We can say that if there is a winning strategy for this isomorphism game, then we can always use maximally entangled state, and we can assume that these positive semidefinite operators, these e's and f's, they are in fact projectors. We can also show that switching kind of input and output, that doesn't change the operator. And moreover, we don't have two sets of operators for Alice and Bob. We can show that Bob's operators can be obtained in a very simple manner by taking transpose from Alice's operators. And because of this kind of standard form of strategies, we can get the following statement. We can say that two graphs are quantum isomorphic precisely when I can find, or what I'm going to call a quantum permutation matrix P of some block size D that satisfies this algebraic equation with respect to the adjacency matrices. And I just want you to compare it with the matrix-based definition of fractional isomorphism and isomorphism, right? Somehow very similar syntactically. I'm just replacing this permutation matrix or the doubly stochastic matrix with now this quantum permutation matrix of some block size. All right, so now what is this quantum permutation matrix of block size D? You can see it as some sort of generalization of a permutation matrix. Now, let me pick this particular definition of a permutation matrix. I want to say that permutation matrix is a unitary matrix whose all entries are either 0 or 1. Now, to get a quantum permutation matrix, all I do is I say that these xij's, now I not only allow them, I don't restrict them to be the scalar 0 or 1, I allow them to be arbitrary orthogonal projections. And if my block size is D, then these matrices, these projections should be of size D by D. So kind of projection is a generalization, right? Kind of 0 and 1 are one-dimensional orthogonal projections. So in particular, a quantum permutation matrix of block size 1 would just be a permutation matrix. Now, one consequence of this theorem is that quantum isomorphic graphs are necessarily cospectral. The way to see it is, well, I look at that, you can see my cursor. I look at this equation, right? And this P that was a unitary, so I can actually say, well, I can conjugate the adjacency matrix tensor identity of one graph to that of the other. And of course, conjugation by unitary doesn't change the eigenvalues, and tensoring with identity changes eigenvalues in some very predictable way. Right? It implies that AG and AH have the same eigenvalues. All right, we can, even though we have defined this quantum isomorphism via this gain, right? We can show that quantum isomorphic graphs are not just two random graphs, right? That they share some similarities. In particular, they have some structural similarities, must have some structural similarities like same diameter, radius, number of connected components, also some similarities in terms of walks, so say a number of triangles, and more generally, the same number of closed walks of any given length. And also some spectral similarities. So not only they are cospectral, but they moreover have cospectral complements, cospectral Laplacians, and so on. And finally, they even have isomorphic coherent algebras. All right, but how do we construct? So I told you a bunch of stuff about quantum isomorphic graphs already, but I haven't showed you a single example. This was one of the, this was probably the biggest challenge when we when we were doing this project. We had proven a bunch of stuff about these quantum isomorphic graphs, and we didn't have a non-trivial example, meaning two different graphs that are nevertheless quantum isomorphic. What do you do if you don't know how to solve a problem? Well, you try to make use of something someone else has done. That's precisely what we did. So we now know how to obtain examples by reduction. So what we did is we took some nice class of non-local games where there's a quantum classical separation, and we found a way how to translate these games, this particular class of game, into graphs. So whenever there's a pair of games like that, I can obtain a pair of graphs that are different, but quantum isomorphic. All right. One other consequence of this reduction, besides giving us examples, interesting examples, is that quantum isomorphism is undecidable, right? So not only that we weren't just smart enough to kind of write a code that will search for examples of quantum isomorphic graphs, it's really that such code doesn't exist. Okay, so here, is the smallest pair of quantum isomorphic yet different graphs. They are on 24 vertices. They don't fit on a single slide, so I'm using 2 slides. I'm just going back and forth. So that's the smallest example that we know of, and I think David will maybe tell you more about how this reduction works. At first, we thought, well, 24 vertices is quite a lot, and there must be smaller examples, but then at some point we realized that, well, actually, I think if you want such an example, it will have like, I forgot what the exact number was, like at least 16 vertices or something like that. So we're not going to get like an example I can easily draw on the board. Okay, so showed you so far is that we kind of started from this, taking this point of view of games, right, and defining isomorphism via a game, and that allowed us to talk about these physics-inspired variants by enlarging the class of strategies that Alice and Bob have access to, right? And then, in particular, we talked about non-signaling isomorphism, and it turned out to be just equivalent to fractional isomorphism and therefore decidable in polynomial time, whereas quantum isomorphism is undecidable. All right, and then we have this chain of implications just because the class of strategies in each case gets bigger and bigger. Quantum strategies is a superset of classical strategies, non-signaling strategies is a superset of quantum strategies, right? And then none of the converses hold. Right? And then we can also have this kind of matrix-based formulation of quantum isomorphism that is quite similar to the matrix-based formulation of isomorphism. Okay. So what I want to do with my remaining time is I want to tell you about a different approach to relaxing graph isomorphism. And the idea here is that I'm going to take these probability distributions that kind of arise from this game, and I'm going to think of them as being in some big matrix. And I'm going to require that the entries that correspond, matrix entries that correspond to losing in this game are 0. So I want to define this K isomorphism matrix. So suppose I have some cone K, and then I'm going to say that a matrix M is a K isomorphism matrix, and this will be a matrix whose rows and columns are indexed by pairs of vertices, one vertex from graph G, one from H, if the following conditions hold. Okay, so these first 2 conditions say that some blocks in these matrices, the entries in these blocks need to add up to 1. And that's kind of trying to capture the like that in the classical or quantum case, this probability, some of these entries correspond to probability distribution, so they need to add up to 1. But depending on the cone that we look at, they might not really. It might not be possible for them to be probabilities because maybe the matrix entries in this cone can be negative. And then I'm asking that the matrix entry corresponding to losing answers is equal to 0. All right. And then I'm going to say that my 2 graphs are K isomorphic if I can find a matrix in this cone K that satisfies all these conditions. The cones that I'm going to look at are the following ones. So the rightmost one is the cone of positive semidefinite matrices. And then DNN is doubly non-negative. So that means you are positive semidefinite and entry-wise non-negative. And then CP is completely positive. So one way to think of PSD matrices is that they are Gram matrices of vectors. So for CP, so for completely positive, I'm requiring that it's a Gram matrix of vectors that are entry-wise non-negative. These 3 cones are kind of very well known in optimization, and people have studied them a lot. This orange one is much newer, and it's introduced by Monique Laurent and her students, and that's called a completely positive semidefinite cone. And that is this consists of matrices that are Gram matrices of positive semidefinite matrices. Okay, so every entry in this matrix can be written as trace of some EI, EJ, where these E's is a list of positive semidefinite matrices. Okay, so it's kind of generalizes this CP cone. All right, and just Oh, okay. And all these cones, you have the following containment. I'm not claiming it's obvious. It can be worked out. You have the following containment, and it's also strict if you take matrices that are big enough. I think 5 is already big enough. And because of this containment of cones, you have the following chain of implications. Right? So CP isomorphism implies the completely PSD isomorphism, and so on. Okay, so the bigger the cone, the easier it is to find a matrix that satisfies some condition. Okay, and then the first thing that we can show is that this quantum and just regular graph isomorphism can be seen as these conic isomorphisms for appropriate choice of the cone. So in the classical case, it's this completely positive case. In the quantum case, is this new cone, just completely positive semi-definite cone. Right? So now let me look at this doubly non-negative and PSD cones. And the nice thing about them is that you can optimize over them easily. Okay, so optimization over this orange cone is undecidable, and optimization over the green cone is NP complete, because you can write things like independence number as optimizations problems over this completely positive. So it turns out that we can have a nice characterization of this DNN isomorphism in terms of algebras. In particular, two graphs are DNN isomorphic if and only if the coherent algebras of the two graphs are isomorphic via some isomorphism that takes the adjacency matrix of one graph to that of the other. Okay, you probably all know what coherent algebra is. For those that don't, let me give a quick refresher. So coherent algebra of the graph would be the smallest coherent algebra that contains the adjacency matrix of that graph. Okay, and an algebra is coherent if the following conditions are satisfied. So I want that the identity matrix and the all ones matrix J is in my algebra, and I want my algebra to be closed under complex conjugate transpose and entry-wise product. Okay. And because of this theorem has some consequences. So, for instance, one of them is that this DNN isomorphism is actually equivalent to the two graphs not being distinguishable by the two-dimensional Weisfeiler-Lemon algorithm. Okay, and we can also test it in polynomial time, just because this two-dimensional Weisfeiler-Lemon again runs efficiently. Now for the PSD isomorphism, we have some similar algebraic characterization like before, but as far as we know, it appears to be a new relation on graphs. So in case of this PSD isomorphism, we need to speak about something that we call partially coherent algebra. Okay, one thing we can show is that this PSD isomorphism, it implies the non-signaling isomorphism. And we can show some properties of graphs that are PSD isomorphic, like they must be cospectral, their complements must be cospectral, their Laplacians must be cospectral. And now the next thing is that if your graphs are sufficiently nice, specifically one walk regular, then actually this PSD isomorphism is equivalent to the two graphs being cospectral. And I want to finish by showing you some examples of separations. Okay, what do I mean by separation? So we have this kind of long chain of implications, right? This CP isomorphism, which is just the regular isomorphism, implies the quantum isomorphism, implies DNN, implies PSD isomorphism, implies non-signaling. Okay, so the question is, do these converses hold at any point? And the answer is going to be no, and I'm going to show you pairs of graphs, kind of starting from here, that show that, oh, this is a pair of graphs that are non-signaling isomorphic, but not PSD isomorphic, and I'm going to go down the chain. So, as promised, non-signaling isomorphic, but not PSD isomorphic. Okay, so these are the same. This is the same pair of graphs, right? They admit a common equitable partition, so they are non-signaling isomorphic. But we know that they are not PSD isomorphic because they have different number of connected components, and we know that PSD isomorphic graphs must have the same number of connected components. Now, this pair is PSD isomorphic, but not DNN isomorphic. So the reason why we know that they are PSD isomorphic is that they are one walk regular and have the same spectrum, right? And we had a theorem for PSD isomorphic for PSD isomorphism that for one walk regular graphs, this PSD isomorphism is equivalent to cospectral, right? And the reason why these graphs are not DNN isomorphic is because they have different radius. So the graph on the left is 4 cubed, so the radius is 4. The graph on the right is a Hoffman graph, and you can convince yourself that it has, I don't know if I said diameter, I meant to say that 4 cubed has radius 4, but this Hoffman graph has radius 3. And if you, I think these two middle vertices can serve as the center of the graph. And now finally, DNN isomorphic, but not quantum isomorphic. So both of these are strongly regular graphs with the same parameters. And actually, we know that any such pair of graphs are DNN isomorphic. That's how we know that they are DNN isomorphic. And initially, to show that they are not quantum isomorphic, we had to work pretty hard. But now we have a much easier way to say why they are not quantum isomorphic. I'm hoping David will tell you the easier way. The way we did it originally is by looking at the quantum chromatic number of the complement and showing that it's not the same. And yeah, it was a rather involved argument. So let me summarize. So I kind of started by taking this game viewpoint, and I talked about this GH isomorphism game. And then I asked, oh, what happens if I allow Alice and Bob to use these quantum strategies with entangled states and quantum measurements? That allowed me to define this quantum isomorphism, and whose further relaxation we also considered this non-signaling isomorphism. All right, and then and we said that this quantum isomorphism and classical isomorphism, we can also see it as these conic versions if we look at the appropriate cones. So a completely positive cone for isomorphism and completely positive semidefinite cone for quantum isomorphism. And then we also looked at the doubly non-negative cone and the set of PSD matrices, and that gave us these two additional relations, and they all form kind of a nice hierarchy of relaxations of graph isomorphism. Okay, and I also showed you examples showing that none of the converses hold. And then this non-signaling isomorphism and DNN isomorphism, they turned out to be equivalent to some previously studied relations on graphs. So fractional isomorphism in case of non-signaling, in case of the non-signaling isomorphism. And for DNN, it was this distinguishability by the two-dimensional Weiss-Feiler-Lemon algorithm. All right, and last thing I want to just summarize is kind of when it comes is in regards to complexity of testing these relations, right? So isomorphism, to the best of our knowledge, quasi-polynomial time. Now this DNN and non-signaling isomorphism we can test in poly time, and that's due to the fact due to the efficiency of these Weiss-Feiler-Lemon algorithms. Now quantum isomorphism, undecidable. There's no kind of published statement about the complexity of PSD isomorphism. We think that it should be doable in polynomial time, just because optimizing over PSD matrices can be done efficiently. That was all that I wanted to tell you, and I would be happy to answer any questions that you have.
So is there any question for Laura? Okay, and nice talk. And sorry, I'm about to fixate on something that's probably like you think is not important, but it's like interesting to me. This quantum permutation matrix or matrices. So yeah, is there any? Do you find that the ranks of these projections tend to be certain things? So in like one dimension, right, the ranks, the projections have to be 0 and 1. And so then it's just the entries of the matrix are 0, or I guess you could do plus or minus 1 if you're just saying these orthogonal projections. So when you start talking about these quantum permutation matrices are acting on things, then like Does it end up being that these projections could be any rank, or is there something about the structure, about the fact that they are, the entire matrix is unitary, that kind of forces them to bend into like rank 0 and rank something else?
Yeah, so somehow in case of homomorphism, you could ask the same kind of question, like, so you also can always pick these measurements to have projections as they are POVM elements rather than just arbitrary PSD matrices. You can ask the same question somehow, can I choose the ranks to be always the same, for instance? And there we know, I forgot, if one of the graphs is vertex transitive, then you can, but in the most general case. Yeah, thank you. Here, we don't have a similar result. Again, okay, I think one thing that one should distinguish is also, can I have kind of a quantum strategy where these ranks are different? Is it possible in principle? Or like, if there is some strategy, can I always kind of uniformize all the ranks to make them the same?
I think both of those are interesting questions to me, at least. Yeah.
But there's no theorem that we have proven that I can just throw as an answer to you. And when it comes to examples, we don't have that many examples. So I think the correct answer is I don't know at this point. But when I was listening to your talk, I was actually thinking, I like how you said, oh, I like to look for nice sets of matrices or vectors and so on. And kind of to exhibit these quantum separations, quantum classical separations in games, that is precisely what you need. You need nice sets of matrices, right? Yeah, I was wondering if maybe some things that some of these examples that you have gathered, like, can I use them to find like new examples of quantum isomorphic graphs or quantum homomorphisms, or just some games with quantum classical separation?
Yeah, thank you.
Yeah. So a question back to you.
Yeah. Oh yeah, you look like you wanted to say something. Yeah, no, maybe we could talk offline.
Yeah.
So for the shrink Hande and row graph, these are the smallest one that are not distinguishable by the Weisfelder-Lemon of second dimension, right?
You're probably right.
I see. So maybe it would be nice to see other pairs of graphs that are, so we can talk about this. But it would be interesting to look at the pairs of graphs that are also smallest and also not distinguishable by the other dimensional Weisfelder-Lemon.
Okay,
maybe
yeah.
Get something.
Somehow, maybe David has some more examples, but somehow we haven't tried very hard to ask, oh, what is the smallest example that shows that the converses don't hold. We just tried to find something, and we're having. I'm by no means claiming that these examples are in any way optimal.
Yep, but maybe just if you want to find more examples, it would be nice to look at the Weisfelder-Lemon distribution.
Yeah, definitely.
So, any other question for Laura?
So the question is basically about what cone corresponds to the non-signaling isomorphism. I was actually I was wanting to guess the non-negative cone, but I don't think that's the case.
We couldn't see it as some conic.
Yeah, but now I think I have a better guess. It could be just the non-negative diagonal matrices, because the non-singly thing corresponds to an LP, and that's exactly what an SDP would reduce to if you wanted. So I don't know if that could lead to something.
Maybe, yeah.
But actually another question is, what happens if you look at, I mean, you showed a bunch of cones, and the cones of SDP matrices is like self-dual, but the other cones, of course, their duals are going to be on the other side. So what happens there?
Good question, Gabriel. We haven't thought about it at all. Yeah,
Right.
but it's a nice question.
Okay, so if there's no more question for Laura, let's thank Laura again.